Hello, I'm Paul Friesen, and in this project for ENGM 360 Computer-Aided Engineering, my goal is to determine the best way to physically model fixed geometry. The part I will be considering is a notched cantilever beam. When creating a simulation in SOLIDWORKS, it is trivial to select geometry to fix it in place. However, fixing one surface physically is not as straightforward. In this project, I will compare physical solutions to this problem against simulation results for this ideally fixed beam. With glue out of the question, I will be testing three beams with additional geometry shown in dark green. The first is a longer beam and can be clamped to a horizontal surface. The second and third are an L-beam and T-beam respectively, which can be clamped to a vertical surface. I will also create digital counterparts of each of these modified beams with surfaces fixed as if held in place by a clamp. The simulation results of each digital counterpart can also be directly compared with that of the ideally fixed beam to predict which physical part will have the most similar performance. To run a simulation, I must apply a material to the SOLIDWORKS part. The beams are 3D printed from PLA, but are not 100% solid, so the known material properties of PLA don't directly apply without modeling the complex internal geometry. Instead, I will create a fictional uniform material in SOLIDWORKS that matches the properties of the 3D printed beam. This fictional material properties do not apply to all 3D printed parts, but just to this particular case. To determine these properties, I'm going to assume that a longer beam models fixed geometry reasonably well, and clamp down an unnotched test beam. By hanging masses from the end and measuring the displacement, I can calculate each trial's effective Young's modulus analytically. The average Young's modulus is approximately 1,470 megapascals. This is 58% lower than the modulus of PLA, so I made the assumption that tensile strength and shear modulus differ from PLA's properties by the same factor. Note the outlier at 50 grams. This shows some nonlinearity in the physical beam's elasticity that will not be captured in the simulations. We can expect the physical models to deflect more than the simulation when small masses are applied. Nevertheless, these fictional material properties prove to be an accurate representation of the material, as the simulation of the unnotched beam matched the physical displacement result within 0.6 millimeters, with an average percent error of 6%. With the material verified, I ran additional simulations of the ideal beam, fixing the end surface and applying a vertical force along a line 5 millimeters from the end of the beam. I repeated this across the same range of masses and with the other beam geometries, recording them in a table found in the appendix. The percent error of the max displacement was consistent across all of the trials, with all of the modified beams deflecting more than the ideally fixed beam, particularly the L beam. These simulations predict the longer beam will produce results closest to the ideally fixed simulation. In each physical trial, I placed the specimen against a millimeter grid and carefully placed weights on a line 5 millimeters from the end of the beam. I took close-up photos to record displacements more precisely. This graph shows the maximum displacement from a SOLIDWORKS simulation of the ideally fixed beam compared with the maximum displacement for the physical longer beam. These trials have an average error of 12%. However, this is skewed by the first three trials, which have an average percent error of 33%, reflecting the physical material's increased elasticity at low deflections. The remaining points are within 3% of the ideally fixed beam. Here is the same comparison, but with the physical results of the L beam. The percent errors are less varied here with an average of 7%. This consistently had less displacement than the ideally fixed beam simulation. The physical T-beam also deflected significantly less than the ideally fixed beam simulation. Interestingly, these both contradict the simulation's prediction that the L and T beams would deflect more than the ideally fixed beam. The decreased deflection in physical trials could be due to the support provided by the fillet, but this feature was also present in the simulations which deflected less. This discrepancy could also be due to limitations of my fictitious uniform material when applied to more complex geometry. This graph compares the signed percent errors for each physical trial. Overall, the L beam, blue, provides the lowest percentage error. However, a better option can be found by changing the physical part depending on the range of forces applied. My final recommendation of a physical analog for the ideally fixed beam is to use the L beam, blue, for small masses and small displacements, and to use the longer beam, lime, for masses 200 grams or greater. Thank you.